In this module, we're going to talk about monatomic ions, that is, ions where there's only one atom, and use the Octet Rule to explain why some ions are more stable than others and tend to form. And we're also going to talk about the sizes of these ions. Remember, the Octet Rule says that in chemical reactions, atoms gain or lose electrons so that they'll have the same number of electrons and thus the same electron configuration as the nearest noble gas. And remember, nearest means the closest in atomic number. So let's look at calcium first. Using core notation, calcium's electron configuration is argon 4s2. The nearest noble gas to calcium is argon, whose electron configuration is neon 3s2 3p6. If we take these two electrons away from calcium, it will have the same electron configuration as argon, and it does. So if we lose these two electrons, we get calcium with a positive 2 charge. Now sulfur, on the other hand, is 2 electrons short of argon's electron configuration, neon 3s2 3p4. So sulfur, to satisfy the Octet Rule, is going to tend to gain 2 electrons to make the sulfide ion. And if these two are in contact with each other and cause each other to gain or lose electrons, then they will have opposite charges. Calcium will have a positive 2 charge, sulfide will have a negative 2, and they'll form an ionic compound, calcium sulfide. Now, the Octet Rule tells us what the most stable ion would be for an element to form. It doesn't mean we can't force these elements to make other ions, it's just that they're not stable, and given the chance, they're going to end up with an electron configuration of the nearest noble gas. So when you take electrons away from an atom to form a cation, remember they always come out from the highest occupied shell, or N. For example, iron, neutral iron, has the electron configuration argon 4s2 3d6. If we were to make the iron 2 cation, we'd have to take 2 electrons away. Now watch. Even though the last electrons we put into iron were the 3d6 electrons, the first ones to come out are the 4s2 because N equals 4 here, N equals 3 here, 4 is bigger than 3. It just ends up that it's more stable to do it that way, and so nature does it that way. So there's the electron configuration for the iron 2 cation. And if we were to go ahead and make the iron 3, we'd have to take one more electron away. And now that comes out of the 3d subshell. And we have argon 3d5 for the electron configuration of iron 3. When you make anions, just follow the same order of filling that you do normally. And that is the electrons go into the next subshell that has room. So for instance, oxygen, its electron configuration would be helium 2s2 2p4. To have the same electron configuration as neon, which is helium 2s2 2p6, it tends to gain 2 electrons. When it does, they just go into the next available subshell. The 2p subshell still has room because it can hold 6 electrons and there are only 4 here. So they go there and we get the electron configuration for the oxide ion. Now the sizes of these ions that form have a pattern to them. And when you take electrons away from an atom to make a cation, you increase the effective nuclear charge felt by the remaining valence electrons because there's less repulsion. And what that means is that the cation that forms is smaller than the neutral atom. Whenever, and this is always true, whenever an atom loses electrons, it becomes smaller. On the other hand, when you make an anion by adding electrons to a neutral element, you're increasing the repulsion, decreasing the effective nuclear charge, and the electrons push each other apart and spread out, and the atom becomes larger when you add electrons. So anions are larger than their parent atom, cations are smaller than their parent atom. And by the way, the more electrons you take out, the smaller it becomes, and the more electrons you add, the larger it becomes. Now, Isoelectronic species, what that is, those are atoms that all have the same number of electrons, but they're different elements. How can that be? Well, you have to have some ions to do that. And for example, this is an isoelectronic series. Fluoride, neon, and sodium cation, all have the electron configuration helium-2s2 2p6, which is neon's electron configuration. They all have 10 electrons. This is an isoelectronic series. But what's different is they have different numbers of protons. The more protons there are for the same number of electrons, the greater the effective nuclear charge and the smaller that species. So the rule of thumb that works is that now make sure this only works for an isoelectronic series, but for species that are isoelectronic with each other, the more protons, the smaller the species. So the kind of questions you tend to see are arrange these species in order of increasing or decreasing radius. That means size. And so if it was increasing, you go neon is smaller than, sodium cation is smaller than neon, which is smaller than the fluoride ion. If it was decreasing radius, it'd be fluoride is larger than neon, which is larger than the sodium cation.